All right, so in doing each of these, of course, the biggest thing to note, especially since we're taking today without calculators, is that we do not actually need to solve for the unknown. All we're doing is trying to decide, would we use sine, cosine, or tangent? That's all we're doing here. All right, so for the first one, I'm going from angle A. I know side A, and I'm trying to find B. So all I need to do is see that it's these three parts that are involved. I can ignore everything that I did not just mark. So from that angle, let's start with this side. What do I call the side A here? Is that the opposite, the adjacent, or the hypotenuse? Well, notice that the arrow is pointing straight across to the opposite side. It's on the opposite side of the triangle. Gee, what do you suppose we'd call it? Yes, it's the opposite. And so side A here is the opposite. Side B. Well, B is the longest side. You'll notice it's also opposite of the right angle. That's enough to tell you right there that side B is the hypotenuse. So at this point, the way we answer the question is we then go back to our notes and we see which of the three trig ratios, sine, cosine, or tangent, involves the opposite and the hypotenuse, because only one of them will. And in this case, it is sine. So the answer here is sine. If you get used to this idea that really that's all we're doing when we set up those equations to actually solve them, you're going to be fine going through and actually setting up these equations. It's just a matter of getting used to this part of deciding if it's sine, cosine, or tangent at the start. All right, second one. We're going from angle A again, and then we have side B, and we want to find side C. So again, we just ask ourselves, what do we call each of these sides? We already know that B is the hypotenuse, so what do we call side C? Well, that would have to be the adjacent. Because remember, A was the opposite, B is the hypotenuse, that leaves C to be the adjacent. And so hypotenuse and adjacent, which one of them involves hypotenuse and adjacent? That is cosine. And I know that by looking back at my notes, or I can remember SOHCAHTOA is a way to remember some of these things. All right, next problem. I have side A, side C, and I'm wanting to find angle A. The fact that I'm trying to find angle A instead of being given it doesn't change how I approach this first step. I still know that everything is relative to angle A. So it's, what do I call side A?
Opposite.
That's still the opposite. What do I call side C? It's still the adjacent. And so then it's a matter of which of the three trig ratios involves the opposite and the adjacent. That would be tangent. The T of SOHCAHTOA. TOA. So it's opposite over adjacent. If I were solving this, then I would say tangent of the angle equals whatever the opposite is over whatever the adjacent is. All right, last one. In this one, you notice I'm switching up the angle. I'm going from angle C this time. We know side A. We know side B. Well, look at the names of each. So this time we're going from angle C. What do we call side A? It's no longer the opposite because I changed the angle. In this case, yeah, it's the adjacent. B, well, it didn't change because the hypotenuse is always the hypotenuse regardless of which angle we're going from. So we got hypotenuse, we got adjacent, so that tells us that we would use which of the three trig ratios? Because cosine is adjacent over hypotenuse. We're also going to practice on this set. And yes, now we're actually dealing with actual numbers in there, but still without calculators. So I want to make sure that we can do these still without calculators. Now, one little note here. I had a typo. I guess I got an autopilot when I put this part in over here. That should be C there. All right, so we want to figure out each of these values. I'm going to go through and show how we would do maybe the first few here. So sine of A. Well, first of all, we're going from angle A. What's the definition of sine in terms of opposite and adjacent hypotenuse? Sine equals what over what?
Opposite.
So yes, sine is opposite over hypotenuse. Got to know it. And so if I'm going to say what sine of A is, I'm going to grab the opposite side length. So go to the opposite side of the triangle from our angle. That means it's got to be the 12. So I put the 12 on the top. And the hypotenuse always goes on the bottom. The hypotenuse here, that's the 20. And so it's going to be 12 over 20, which, yeah, is correct, but it's not totally done because that fraction can reduce. I know you don't have a calculator, but you can reduce these. Because what can I divide both 12 and 20 by?
2.
Okay, 2. If I divide both by 2, that gives me 6 over 10. That reduces even more. I can divide top and bottom again by 2, which would give me 3 over 5. Yes, some of you saw we could have divided top and bottom there originally by 4. That might have even been better because it could have gotten us to the same place a little bit faster. But either way, as long as you get to 3/5, you're in good shape. Now, having seen how we did that first one, go ahead, do the rest of those, please. So for the next one then, if I'm going to do cosine, our definition from our notes is adjacent over hypotenuse. And so if I'm going to go ahead and fill this in, then the adjacent side length to A, that's the 16. So I do 16 over the hypotenuse, and the hypotenuse hasn't changed. Hypotenuse is still 20. And I reduce that. Notice top and bottom still divisible by 4. And so if I divide top and bottom by 4 to reduce, I get 4/5. All right, next up, tangent of A. Tangent, remember, is opposite over adjacent.
I've seen that.
And then the opposite length is still 12. The adjacent length is still 16. If I reduce that, that becomes 3/4. The rest of these all follow the same basic pattern. So sine of C, the only difference is you have to remember that when we switch angles here to go from angle C, that the opposite and the adjacent have just switched places when I switch the angle. The hypotenuse is still the same though. So sine of C then is going to be 4/5. Cosine of C will be 3/5, and tangent of C is now 4/3. Because I just switched the opposite and the adjacent, and so that changed those corresponding parts in sine, cosine, and tangent as well. All right, so then, having done these are basically the practice and review from stuff we did earlier in the week. We do have to introduce one new thing that we haven't done this week at least. We can't go a whole week without fractions, right?
Oh, yeah.
And we've done all sorts of things with fractions so far. We dealt most recently by turning improper fractions into mixed numbers. Well, today we're going from mixed numbers into improper fractions, which actually in some ways is a lot easier, as we'll see. Now, like all the fraction work that we've been doing, we normally start by taking a look at a picture of it. So, in order to visually see what's happening when we see 2 3/5, this is how I'd actually draw that out. Where you'll notice that each of those 2 completely full rectangles basically represents a whole. So that's like a whole 1 and a whole 1. So that's where the 2 comes from, because we have 2 whole numbers there. And then that last fraction, well, we cut our whole up into 5 pieces, and we shade 3 of them. So this is really what 2 3/5 means. Well, if I'm going to turn this into an improper fraction, basically what I'm doing is I'm counting how many fifths, individual little pieces that is, do I actually have shaded. And so you'll notice that there's like 5 in the first bar and 5 in the second bar and then 3 in the third bar. So there's a grand total then of 13 fifths shaded. And so that's the improper fraction, it's 13 fifths. Okay, that's all right. But oftentimes there's a little bit of embedded insight into this that some people don't notice when they've struggled with this and they don't quite see something. So let me make it a little bit easier to see. What if we take 10 2/3? If I tried to approach 10 2/3 the same way that I just did the last one and draw it out first, that means I have a lot of whole bars. Do I really want to have to count every single one of those pieces individually? No. Do I want to have to do 3 plus 3 plus 3 all the way down? No. If I want to note how many total bars are shaded in that section there, I would just say, well, I have 10 bars, and each of those bars has 3 shaded pieces to it, so that tells me the 30. This is actually the technique that we do when converting a mixed number into an improper fraction, is we multiply the whole number by the denominator. And that's why, because it tells us how many wholes we have. How many of those little pieces are represented in those 10 whole numbers. But then, that's not the whole story though, because the answer isn't just 30. I still have the 2 that are hanging out there. So I end up doing the 30 plus the 2. And so we get 32 thirds. And that's actually what we're doing in order to do any of these problems. Anytime you want to take a mixed number and turn it into an improper fraction, multiply the whole by the denominator, and then add that number to the numerator. Now I want to practice this idea. Please take these 2 mixed numbers, write them as improper fractions, and these are going to be the last 2 bits of practice we do today. So for the first one, fairly straightforward process that we're going to follow those instructions. I first multiply the whole by the denominator, so I do 2 times 7, which gives me 14. I then take that number, so I take the 14, and I add the numerator to it. So I add it to the top basically, and that gives me 20, which tells me that my final answer is going to be 20 over, it's always over the same thing, so it's over 7. Now that being said and done, we go on to the second one, and on the second one, did you notice there were actually a little bit more depth to it? On the second one, if I just follow the same procedures, I can go ahead and do 5 times 8, which gives me 40. And then I take that number, so I take the 40, and I add the numerator to it, so 40 plus 4 gives me 44. That tells me my new numerator. It tells me it's going to be 44 over 8. But I hope that you notice that that can reduce. What can we divide both 44 and 8 by? Well, I could divide them by 2, but there's something even better than that. I could divide them both by 4. And so I actually want to reduce that and turn it into 11 halves. But now, I did it that way because that's following basically the same process what we've always used in the past. But I want you aware you could have actually done this in a slightly different order. You could have actually started by reducing. So we could start by turning this into 5.5. And then having done that, we could do 5 times 2 equals 10. And then we do the 10 plus the 1 to get 11 as our new numerator. And so we get an answer of 11 halves that way. Either order you do it in is fine, but make sure that you do, in fact, reduce your fractions. Every single time you have to reduce your fraction.